Hello, everyone.
Hello, Dr. Shaw.
So today I'm going to continue about the partial correlation. So in the last time we talked about the multivariate distribution. So we have a multiple variables, and we have looked at the mean vector and covariance matrix. And then the covariance matrix has a structure with the diagonal part is the variance, and then off diagonal part is the covariance of the pair of the variables. And the correlation that the diagonal part is the the off diagonal part is the correlation of the um, two variables. And we also look at the properties of the covariance matrix and properties with the linear combination of the random vectors. And we have looked at the multivariate normal distribution, and um, and the multivariate normal distribution has many good properties. So first property is its linear combination is still the normal distribution, and then if their correlation is or covariance is equal to zero, that's the equivalent to say that they are independent each other. Then their pairwise independence is the implies the mutual independence. So we define the partial correlation, which I would say is more appropriate to call the conditional correlation, where we would like to see relation between x and y given the information of z. And we also see that there's a discrepancy between simple and partial correlations. They may not be same direction. They may even be opposite, have opposite signs. We have looked at the example. And then now today I'm going to talk about the inference for the partial correlation. So we have the partial correlation, and we talked about the partial correlation, which is the population quantity, which is the parameter. So this rho xy dot z and rho xy, rho xz, rho yz, they are all parameters. So we need to estimate them when in practice. So by replacing the rows by the r's, so we replace the simple correlation population correlate simple correlation by the sample simple correlation, which is the correlation between x and y, sample correlation between x and y, sample correlation with x and z, and sample correlation with the y and z. And then we would like to test whether the rho xy dot z equal to 0 or not. Then the test statistic is the sign of rxy dot z. So sign means that it returns the sign of the number in the parentheses. So if this rxyz is the positive, the sign is the 1. The r is the sorry, if the sign is going to be the plus. The if if it is negative, then it returns the negative value. And the times the square root of rxy dot z squared divided by r minus 1 minus r squared rxy dot z squared times df, where the df is the degrees of freedom. So here we have the n minus 3 rather than the n minus 2 because we have another variable. So we have to minus 1 from the n minus 2 because we lose the 1 degree of freedom by estimating with correlation with z. Then if the absolute value of t is greater than the t value with n minus 3 of degrees of freedom, and then probability alpha divided by 2, then we reject the null hypothesis at the 100 times alpha percent significance level, where the null hypothesis is that the rho xy dot z is equal to 0. So we are doing um, testing whether the relation between x and y is whether fully explained by z. So if we do not reject, then we have evidence that the relation between x, y, z is fully explained by z. Um, um, or if we reject them, then we may say that the relationship between x and y, z may not be fully explained by z. So the confidence interval, so we build the confidence interval. We, as we did in the simple correlation, we applied approximation. The transformation of g of r x y dot z is the normally distributed with the uh, g rho x y dot z with the 1 over n minus 4. Approximately, and then the g function we used in the simple correlation is the inverse of the hyperbolic tangent, which is the arctangent. So the approximate confidence interval for v is the v1 and v2, and so which is uh, the arctangent of rxy dot z minus the gi power 2 times the square root of the 1 minus n over 4. So that's the lower bound, v1. The upper bound, which is the v2, is the arctangent of rxy dot z plus g alpha divided by 2 times square root of 1 over n over 4, n minus 4. And interval for rho xy dot z is the we transform this lower and upper bound back to original scale, which is we apply the uh, hyperbolic tangent function on in each endpoint. Any questions so far? So basically, the hypothesis testing and constant interval calculation um, is not very different from the simple correlation. Basically, for in the partial correlation, then uh, these hypothesis testing and constant interval uh, they are an extension of the what we did in the partial in the simple correlation. So let's look at the example. So we have sample with the size 100 children, and we record variables. The, the one is the reading comprehension score, and the y is the body weight, and then this third variable is the age. And then we compute the sample correlation matrix, which is the diagonal part is still the 1 in the sample correlation matrix, and the off diagonal part uh, consists of the value of the sample correlation of the pairs. So the sample correlation between x and y is the 0.616, and sample correlation of x and z is the 0.827, and sample correlation between the y and z is 0.732. And then if you take a transpose of the each term, I mean they are the same. For example, rxy is equal to ryx, so that we have the same value on the this ryx part. And then the question is, does this suggest that children's reading will tend to improve if they gain weight? So basically, we are looking at the correlation between x and y. But here we need to consider effect of z on here. So can anybody answer with this question? So how do we need to deal with this issue, this question? Okay, so yeah, Brenda says a very good point. So age is what causes the reading score and weight to increase. Anyone else?
Um,
Yes.
yeah, so maybe if we know that age is a confounding variable, what we can do is hold age fixed so that we try to control the effect of age on both children's reading and their gain of weight gaining.
Yes, that's a very good point. So we have to control the effect of the weight, effect of the age here because we can see that the we have a very high value of the a correlation between body weight and age and reading comprehension score of the age with age. So, and then this high correlation between X and Z and Y and Z is very um, uh, is sensible. I mean, it makes sense because as aging grows, usually your reading comprehension ability increases. And the body weight also increases by the age increases. So here, so the we calculate the rxy.z, which is the sample correlation, partial correlation of x and y given the z. So in this case, excuse me, we get the the partial correlation value is 0.028, and then the corresponding the t statistic is you can see that it's very small, 0.276, and then the partial correlation value is not significant at 5% level. So which implies that the children's reading will not tend to improve if they gain weight, which also means that the this relation between the children's reading and then um, and then the relationship between the children's reading and then gaining weight, they are explained by the age. And another way to compute the sample correlation and z is the first we regress the x on z and save residuals, and we regress y on z and save residuals, and we compute the simple correlation between two sets of residuals. So here we regress x and y, x on y, x on z, and y on z, which means that we firstly look at the correlation relation between x and y, sorry, x and z, and then so we save the residuals, so which means that we have the unexplained part x and between x and between z. We have saved the unexplained part from the regression or relation between y and z, and then there are an unexplained part. Now we calculate this the simple correlation. So here we remove the effect of the z on these residuals. So we are basically controlling effect of z. So partial correlation is actually is same as the simple correlation with the two residuals, because by having these residuals, we are removing effect of the z. Okay, then let's look at the example. So here I have the data x and y, and then here I generate the random variable z from the normal distribution with the mean 20 and then standard deviation 5. So this is the this is the third variable, and we can calculate the correlation of the x and y, x and z, and y and z. And we can compute the partial correlation of the rxy.z. And then when you run this, you can calculate, you can get the rxy.z. So we have a very high value of the partial correlation. So we can do the hypothesis testing on here. So our n, if you look at the n on here, we have a 15. So by applying the formula of the test statistic, which is the sine of the rx.z times the square root of the rxy.z square divided by r minus rxy.z square, and then times the n minus 3. That's the test statistic. So when you calculate this test statistic, Then we have to compare this with the t value, and if you use the 5% stiffness level, the t value with the degrees of freedom 12, which is the 2.178, 179, and the test statistic, the absolute value of test statistic, the same as the original test statistic. And this is greater than the t-value, which means that we reject the null hypothesis that the partial correlation is equal to 0, which means that the relationship between x and y may not be explained fully by the z. And then here this makes sense because the z is the independently generated from the xy. Z is not a function of the x and y, so it's it is sensible to have we have this high value of test statistic and a significant result. And then we can calculate the confidence interval. First, we have to transform our xy.z to quantity that we can apply the normal approximation. So we apply the arctangent hyperbolic tangent, which is the as we did in the simple correlation, we apply this hyperbolic arctangent, the minus 1 point, and then we apply the 1.96 times the square root of 1 divided by n minus 4. So this z dot low is the lower bound of the confidence interval for this transformed value, and z dot high is the upper bound for the transformed value, and then we apply the original scale on these endpoints to obtain the confidence interval for original low xy z. So we run this code. You can see that the with the 95% confidence, the partial correlation, the population partial correlation is the between 0.83 and is in the between the 0.83 and 0.98. And this interval does not contain the zero, so we can also conclude that the partial correlation is significantly different from zero. And then, as I said, we can compute the partial correlation in a different way. So we, as I said, we can first run the regression x on z and store the residuals, and run the separate regression y on z and store the residuals from the second regression, and we calculate the simple correlation between the two residuals. So you run this, you can see that this is identical to what we have as the rxy.z. Any questions?
Yes, sir, I do have a question.
Yes, go ahead. Yeah.
Yes, actually, I just want to know, this video will be available before Friday or before?
Sorry, what's your question?
I was just asking if this video will be available before Friday.
Yes, this video, you mean the video will be available on the Friday. Yeah, before
Yes,
Friday. Yeah. So the next topic is about partial correlation. Is suppose that we have a two continuous variable, and we have a third variable is non-numeric grouping variable. So we want to calculate the condition of correlation between x and y given the uh, grouping variable, usually the categorical variable. For example, suppose you collect the information uh, on two questions from a sample of likely voters. So X is the in the next presidential election. How likely are you to vote for the Republic? So 1 is the very unlikely, and 5 is very likely. This is the so-called Likert scale. So in the social sciences, sometimes the people treat this the continuous variable, uh, and then you can then compute the correlation between. They used this Likert scale to compute the correlation between the variables. And then the Y is the what was your income in the last year. The correlation between these two variables in your sample may be positive, but here we have to consider the one confounding variable. I mean, there may be many confounding variables, but one of the confounding variables that we can think is the geographic areas, because within the same the geographic areas, their the income that within this geographic area that they have a similar income, and then within the geographic area they have the same um, political opinion. So so if you compute the average value of x and y within the geographic areas, however, the correlation between these average scores would be negative. So we have to consider the geographic area as a confounder, and then we have to compute the partial correlation controlling the effect of the geographic areas. So here it is difficult to use the our original method, which is applying the formula, because the z is not the I mean the geographic area is not the numerical variable. So here that we can modify the approach that we did that in the as we just discussed, which is the using the so we can I mean let me talk okay, let me back up. So we have to consider the removing the effect of the geographic area by doing as follows. So we subtract each subject's value of x and the mean value of x for his on her geographic area. So we calculate the the mean value of the x on the geographic area. And then we do the same thing on this y. So we calculate the mean value of the y, which is we subtract the subject value of y minus the the mean value of the y on within this geographic area. So by doing this first two steps, you can remove the effect of the geographic area. And then we can calculate the a simple correlation between these mean values of x and y. So we can calculate the partial correlation of x and y given the geographic area by using this mean values of x and y. So this is the particularly useful in many cases because you can remove the effect of a confounder where the confounder is being a non-numeric value. And then the extension of this is actually we can use the dummy variable approach in the regression. So we will discuss the dummy variable in the later in this semester. But for here, I would like to say in the partial correlation. So if you have the third variable, your third variable is non-numeric. And then if you want to control the effect of the third variable, then you can use this d-mean, the correlation between these d-mean values. Any questions? Yeah, let's talk about the questions about the recording and the other thing in the end of the class. Is it okay? Okay, now let's move on to the topic on the multiple linear regression. So we have discussed the simple linear regression. However, in practice, the simple linear regression modeling is rare because we often have more than one predictor. So as I said in the last time, we often have the one more predictor in the data set. For example, if you want to model the association between the GPA with the your predictors, then you can think about many possible predictors. You can think about study time, and you can think about sleeping time, or you can think about age, you're thinking about the gender, you can think about their social economic status, and etc. So there are many predictors that we can use to make a prediction for the outcome, or the think about the make an association with the outcome. So simple linear regression is not very practical in many cases. And the second thing is that the relationship between the response and the predictor may be nonlinear, which means that the response and predictor, they are linear combination. In that sense, in that case, it's a linear, but it can the predictor may not be the original scalar predictor itself, but maybe it's gonna be square of the predictor, or the square root of the predictor, and etc. So sometimes these two issues are related. Even if you have just one predictor, but its relation between the response is nonlinear, then you may need to create two or more columns in the X to characterize its effect. And this nonlinear relationship cannot be fully dealt with until we understand what happens with the multiple predictors. So so we would like to talk about this multiple linear regression, which is that we model the response by the multiple predictors. And then this is very important theoretically and also practically. So we define the X to be n by p matrix with the rank p, where so you have first column you have ones, so which is that the we have the intercept. So as you will notice in the matrix multiplication that I'm going to talk about just later, and this ones takes a role to have the intercept in the multiple linear regression model. And then we have x1 to xp minus 1. So we have a p minus 1 predictors. So we have p minus 1 predictors, and then the x1 is the column of the second column of the both x. And then x2 is the third column of the both x, and then xp minus 1 is the both column of the pth column of the both x. And then sometimes x is called design matrix. So it is the, you can think of this as bold X is the matrix of predictors. But if you look at the other linear regression book, then sometimes the people call this bold X as the design matrix. Now, this bold X can be any type of data. It can be continuous, it can be categorical. So as I said, we are going to talk about the how to do regression on the categorical variable case. So in theory, and I mean, it can be any type of the data, continuous and categorical. And bold data, which is the column vector, beta 0 through beta p minus 1 is a p times 1 vector. And the epsilon is the bold epsilon is epsilon 1 to epsilon n. It's n times 1 error vector with bold epsilon follows the multivariate normal distribution with the mean 0 and then sigma square times the in, where the in is the n times n identity matrix. And then the outcome y is the y1 to yp. Question so far? Okay, then I will move to the next topic. So the model is the y is equal to x beta plus the bold y is equal to bold x beta plus epsilon. And here we can do a matrix multiplication on this bold x and bold beta because the bold x is the n times p matrix and bold beta is the p times 1 vector. And then so we have n times 1 vector from this multiplication, and the bold epsilon is n times 1. So the degree, the dimension matches here. Then we call this model multiple linear regression model. And without matrix notation, the model is yi is equal to beta 0 plus beta 1 xi1 plus beta 2 xi2 onto beta p minus 1 times xi p minus 1 times plus epsilon I. So this one is the what you may have seen in the undergraduate the statistics courses for a multiple linear regression model. So this version is the expansion of the this matrix form. So in each row, you have the y I is equal to beta 0 plus the, in the ith row, then you have the yi is equal to this beta 0 plus beta 1 xi1 plus until plus I. And then the interpretation is that, so beta 0 is the expected value of outcome when the beta 1 through beta p minus 1 is equal to 0. Sorry, the xi1 through the xip minus 1 is equal to 0. Okay, there's a typo here. I'll fix it. So this is the expected value of outcome when the all the predictors are equal to 0. As I said, in the simple linear regression case, this interpretation of beta 0 is not very important, and sometimes it's not very practical because it is difficult to have a predictor value being exactly 0. For example, weight or height cannot be exactly value 0. So if you have predictor weight and height in your model, then beta 0 does not have a practical meaning. And then beta j, the j equal to 1 through p minus 1. So when 1 unit of xj increases, the average value of the outcome changes by beta j under the condition with fixing other predictors as constant. So here, in linear regression, we do not have to worry about existence of the other predictors because there is only one predictor. However, in this multiple linear regression model, we have the many predictors, or I would say multiple predictors. So you have to control the effect of the other predictors. So here we will interpret that by fixing the other predictors as constant, and then 1 unit of the xj increases, then the average value outcome changes by the beta j. So the expected value of y given the xj is given x is the when 1 unit of xj increases, then we fix other predictors as a constant, and then we only look at the changes on this xj in the macro interpretation with respect to beta j. And there are the assumptions. So both x is treated as a non-random. This is the same as case in the linear regression. And the sigma square is the constant. So sigma square is not a function of the predictors. So the sigma square is constant. So the sigma square is that's gonna be same across all the observation. And epsilon I is independent with each other. And then both epsilon has a normal reduced with mean 0 and sigma square in, which means that epsilon I is the normal distributed with the mean 0 and sigma square. So this means both epsilon is the multivariate normal distribution, and then this epsilon I, which is this single random variable, is the normal, just the standard has a normal distribution, univariate normal distribution with the mean 0 and the variance square. And then if you see that both epsilon has the diagonal matrix, which means that with the normality assumption, which indicates that the epsilon I is independent of each other. and then somehow you or assume both x as random, then if we assume that this both epsilon is uncorrelated with every epsilon of x. So this both epsilon is the leftover of the modeling this both y on this both x. So there's no systematic part of the model in this epsilon if the our linear model is the correctly specified. So here this the fifth one. This is also important on this model checking. And then for details of model checking, we will discuss on the later in this course. You can now just think that if you can treat it in the both x as non-random, that's totally fine. And if you somehow assume both x as random, then this we have to add one more assumption, which is the epsilon. Both epsilon is uncorrelated with every element of the design matrix. And then by using the least squares method, we would like to minimize. So here we would like to minimize this Q, which is the matrix multiplication. So y minus x beta, which is it can be the error term. The error term transpose the error, which is that the sum of the epsilon I squared, and then here the Q is the so here the one question that I would like to ask is what is the dimension of Q? Okay, anyone else? So Rao, can you tell me why is n by p?
I would think because we have n observations and p predictors.
Okay, then Brenda, can you tell me why is 1?
I'm honestly not sure. I just took a guess.
Okay, that's fine. Yeah. So I mean, yeah. So Brenda is right. So it's a 1 because if you look at this y minus x beta transpose is the 1 by n because this both y minus x beta is the n by 1, and when you transform it, it's going to be 1 by n. So this y minus x beta is the n by 1. So you do a matrix multiplication on 1 by n and n by 1, so you have 1 by 1. So dimension is 1. So let me write down here. Is this clear? Okay, so and then when you expand this, the non-metric term, then it would be a little bit this long equation. And then now, as we did in the simple linear regression, we take a derivative with respect to beta and this both beta with this, and setting to 0. So this we take a derivative with this q with the the vector beta, and then you can get the 2 times the x the transpose y minus x beta is equal to 0. So since we take a derivative with respect to both beta, and the beta is the p times 1 vector, so we have the also the vector which is the p times 1 vector here. So then you can remove this 2 because it does not minus 2 because it does not affect this 0, and then this x transpose y is equal to x transpose x beta, which is the normal equations in the multiple linear regression version. So in normal equation, the simple linear regression, is we have only two equations. Now here we have the multiple predictors. So, and we have the since we have the p unknowns and we have a p equations in here. And then the solution is the beta hat is equal to x transpose x inverse x transpose y. And then we can also estimate the sigma squared by the y minus x beta hat. It should be beta hat. So y minus x beta hat transpose y minus x beta hat divided by n minus p. And then for the simple linear regression, this normal equations become, so this is the x transpose x. And then in this simple linear regression, we have the beta 0 and beta 1. So this x transpose x would be 2 times 2 because the x is, in that case, x is the first column is 1 and the second column is the axis. And then if you, so it's a p by 2 matrix. And then if you make a transpose on that x, then it's gonna be 2 by p matrix, and then dual x transpose x, and that's the 2 by 2 matrix. And then this one is the our beta vector is the 2 by 1. And then here this x transpose y is the also the 2 by 1. Because the in that case x transpose is the 2 by p. Sorry, this here the x. Yeah, so x transpose x is the and the 2 by 2, and then the beta is, and then the here the our normal equation. Here we have the xy, which is the sorry, this is just let me back up. So this is equal to the x transpose y, because the x transpose is the 2 by n and y is n by 1, so it's going to be by 1 here. And then this beta 0 hat and beta 1 hat is the you can get the 2 by 1 vector, and the sigma square hat is the which is the which we express as the EI as this the residual, and EI is the sum of EI squared divided by n minus 2. And then this is the both epsilon is the normal distribution with the multiplied normal distribution, the mean 0, and the variance, the sigma 0 times the identity matrix. And my question is the what is the distribution of the board y? So remember that the bold y is the bold x bold beta times bold beta plus the bold epsilon. So what is the distribution of the bold y? Yes, Rao?
Would it be normal with the mean x bold with a beta coefficient matrix with a variance with a sigma squared matrix?
Okay. Okay. Does everyone agree with the Rao's opinion? Because so we have a bold y is equal to bold x bold beta plus the bold epsilon. And the variance of the bold y, so here the bold x is treated as non-random and the bold beta is also non-random. So only random part is this bold epsilon. And then if you remember the property of the variance, the constants does not affect the calculation of the variance. So the variance of the bold y is the same as the variance of the bold epsilon, which is the sigma square IN. And then for expectation of bold y, since the expectation of bold epsilon is 0, so we only have the constant part, which is the bold x times bold beta. And then the normality is preserved when we have a linear combination of the normal distribution. So this bold epsilon follow have the multivariate normal, and the x bold x bold beta, they are the constants. So this summation is still the multivariate normal distribution. So that's why we have a bold y has the multivariate normal distribution with the mean x beta with the variance sigma, the variance or the covariance matrix is sigma squared times IN. Okay, so I will stop my lecture here. And then for the persistence question, then I think I record the September 23rd lecture. So it will be available, I think, today. And then I would like to say that please keep in time in the lecture time. So our lecture is 1:30, but sometimes I think some students they come in late. But I would like to start on time. So please keep keep time on lecture start. And then the practice problem is available on the Blackboard, so you can download it and then start to work on it. And then homework 3 is also available, and it's a very short homework. It's only big 2 problems, and then that's due on this Friday. And then the solution will be that homework 3 solution will be available after you submit the homework 3. And then, as I said, that this Thursday I will go on the practice problems in the office hour time. Any other questions? Okay, if you don't have any questions, then I will stop here. Then I will meet you on this Wednesday for lecture. And if you have any questions, you can come to my virtual office hour on Tuesday and Thursday. So if you have any questions, then you can ask on the virtual office hour tomorrow. Okay, then I will see you on Wednesday.